Okay, so if you guys click the chat box, you'll have a PDF of the one that I sent you guys. Okay, you guys ready? Okay, I take that as a yes. Okay, so let's start off with the first question. Can you guys see my screen?
Yes.
Okay, so which of the three major subatomic particles have a mass of approximately 1 unit? Okay, our first one is E minus, standing for electrons, P plus, standing for protons, N zero, standing for, or N naught, standing for neutrons. So which one do you guys think it is? You can put your answer in the chat box, or you can say the answer.
Would it be proton?
That is true. Is there anything else? So that one would be correct, sorta, but not only proton.
Would it be electron?
No, not the electron.
So no.
Electron's weight is very low. It's actually one 8,321 of a proton. So it's really tiny. It's like a speck of dust on a person's body.
So it would be the last multiple choice.
Right. So the neutron and the proton. So the weight of your atom is going to be made up of both the neutron and the proton. Okay. And so each of them are about one mass unit. Is this, you said it's zoomy? It's do you want me to go in a little bit closer? It's a little blurry on Zoom. Is that better? Is that better, Rosa? Okay. Okay, question number 2. Two natural isotopes exist for silver. 51.83% of the atom has a mass of 106.90509 units, and the remaining fraction has a mass of 108.9047 units. Calculate the atomic mass of silver. Okay, so the easiest way to kind of think about it. So when we're talking about isotopes, we know that isotopes are just, excuse me, are just examples of atoms that have different masses. So they're the same element, but they weigh differently. Sorry about that. Um, so when we look at the mass on the periodic table, it's just the average of all of the different isotopes that exist. So all we have here are the two different isotopes that exist for silver. So one of them is going to weigh 106.90509. So what we're going to do is,
We can't see your screen.
oh, you
Sorry.
can't see my screen? Okay. Sorry. There's also something going on happening with my computer here. Let's see. Okay, there we go. Let's see. Can you see it now?
No.
Okay, that's not doing good. How about now?
Yes.
Okay. Okay, sorry about that. So, oh, so when I left, it actually took it off the screen as well too, the question?
Yes.
Okay. Sorry about that. So 51.83% is going to be how much we have of our 108. So we're going to multiply that by that 58, that number by that 58.83. And we want to remember that that's going to be percentage because it's going to be important towards the end. So, okay. And then the 108 is going to be that remainder. So if we assume that we have 100%, which is what we're going to have, we're going to subtract that 51.83. So that's going to be 48.17%. Okay. And so we're going to have our 108 9047, and that's going to be multiplied by that 48.17. I'm just going to put the times there. Okay. We're going to take these values, we're going to add it together. And then we're going to divide this entire thing by 100 because we're making an assumption that it's about 100% of it. And then that should give us our value. So we're going to divide that by 100. And if we look earlier, even though we're adding this up, so this guy should have given us 4 significant figures. This guy should also give us 4 significant figures. So our number should just basically be this number here in terms of our sig figs. So at the end, we end up with 107.87. For the units or the atomic mass of our silver. Okay. So remember, you're going to use your either your fraction or your percentages relative to each mass. And then essentially after you've done that, you're going to add them together. And then in this case, because we use percentages, we have to divide it by 100. And then that would give us our value because 100% is the total amount that we're taking into consideration. Okay, questions?
What chapter is this from?
So this was chapter 5.
Okay, thank you.
Okay, which of the following statements is false? Atoms of the same element, let's say atoms of the same element that have different masses are called isotopes. The second one, the mass of isotopes vary because they are different. They have different numbers of electrons. The third one, the mass number of an isotope is the total number of protons plus neutrons in the nucleus. Fourth one, you can find the mass number of an atom given the number of protons and the number of neutrons, but without it, let's say, without being given the number of electrons. The fifth one, every atom of a particular element has the same number of protons. Okay, which one do you guys think? Again, you guys can put it in the chat window if you're not comfortable yelling out. Oh, yes. Okay. So for those who didn't get okay, so I sent you guys the practice exam that I'm currently using that you guys can follow along for those who didn't get it earlier. Hi, Soul, how are you? So I'm not doing too bad, just a little tired. I don't believe in sleeping these days. Trying to get caught up. So, do you guys have some answers for me? What do you guys think?
I'm gonna guess C.
You're gonna guess C? Okay. So, anybody else wants to take a guess? Okay, so we have 2 for C. I have a B. Okay, so and I have a couple of C, another C. Okay, so the answer for this question is actually B. That is the one that's false. Okay, because we know that earlier we were talking about the mass of the atom, that it's consistent of just the protons and the neutrons. So the electrons are so light that they're not going to affect the weight of it. So the isotope's mass is not going to be affected by the number of electrons. It's only going to be affected by neutrons. So the first one is correct. That one is true, I should say. C is also true. Total of protons and neutrons. So the only one that's false is that one, B. So good job for those who said B. Okay. Here is the fourth question. I'll read it, and I'm trying to multitask here in the background, so bear with me. Okay, so it says, which of the following symbol slash pair name pairs is slash are correctly matched? Our first choice is FL, fluorine. Our second choice is N, neon. Our third choice is S, sodium. Our fourth choice is CH for chlorine. And our fifth choice is H for hydrogen.
So only hydrogen.
So only hydrogen. Do you guys all agree with that? Okay, so that is correct. So it's only the last one. Okay, so the next question, it says, let's see, one of the main features of Dalton's atomic theory, no longer considered valid, is atoms can be created or destroyed. Which of the following, which of the following is the best example of why this feature is no longer considered valid? You get some time to think about it. Which one do you guys think? See, I see an E. Okay, so let's think about what it's asking us right here. Okay. So do you guys all agree it's E? Okay. E it is. That is correct because subatomic particles were discovered. Good job. Okay. So which of the following is correct? The element H is in both the first period and the seventh period. The element in A is in group 2A/2. The element GE is in the fourth period and group 4 or group 14, group 4A or group 14. The element CR is in the third period, group 6B and group 6. More than one of the statements above are correct. Okay, let's pull up the periodic table. So we have sodium. Sodium is in group 3. Is in period 3, group 1. So that would mean that answer is incorrect. So we know that that one isn't right. What about GE? Where's GE located at? Okay, so GE is in the 14th, group 14, period 4. So is that correct? Period 4, group 14. I see some yeses. Um, let's see. What about element CR, chromium? Chromium is in group 6 and period 4. Okay, so that one isn't correct. And the last one, no, sorry. The last one, so we know, well, let's talk about the element H, is both in the first period and the seventh period. So we know that hydrogen is not both in the first period and the seventh period. So we know that the correct answer is only the third one. So C. Okay. Ready for the next question?
Yes, sorry, I didn't get the answer for the last one. I had to step out a little.
For 6
Five.
or for 5? Or 5? Okay, now my computer's trying to act up. Okay. So the answer is the discovery of subatomic particles. So it's the last one.
Okay, thank you.
Okay. Let's go to the next question. So which of the following statements is false? A chemical change that releases energy to the surroundings is called an exothermic reaction. B, a chemical change that absorbs energy from the surrounding is called an endothermic reaction. C, Sodium plus fluoride yields sodium fluoride plus energy, is an example of an exothermic reaction. B, 2A2B plus energy yields 2A2B2 plus B2, is an example of an exothermic reaction. All the above are true. We have a D. We have a D.
I'm gonna go with D as well.
Okay, we got 3 Ds. And we got another D. Okay, 4 Ds. So I'm going to say that you guys are pretty convinced that it's D, right? So that is the correct answer. So we know that this is an endothermic reaction because energy is being put into the system. Or you could say energy is being absorbed into the system, into the reaction from the surroundings. So in that case, it should be endothermic instead of exothermic. You're correct. That one is false. Good job. Okay, let's see. Next question. It says, which of the following is/are endothermic for the underlying object? Because we always know that it's going to be relative to what you're looking at. In one case, it could be endothermic, or in the other case, it could be exothermic. So it depends on the perspective. Okay. So a baked potato, or sorry, baking a potato. Do you guys think that that is endothermic? The potato being baked?
No.
No. So what's happening? Are you putting heat into the potato when you're baking it?
Yes.
So wouldn't that be endothermic?
Yes.
In? Okay. That one is a yes. So what about a person being burnt by a pan?
Yes.
Yes. Okay. What about a wood log burning?
No.
No? Okay. What do you guys think? Okay. Exothermic. Okay. Okay. So in the case of the wood log burning, wouldn't that be releasing heat? That one? So it would be exothermic. How about a lit? How about a lit light bulb shining? Endothermic or exothermic?
EXO.
Exo. Okay. So we know that those two are going to be exo. And what about a person digesting food?
EXO.
Exo. Yep, exo. Okay. So our correct answer should be 1 and 2. Okay. The next one. Okay, let's see. A book is pushed off the table and it falls to the floor. Which of the following statements about the book is false? A, its potential energy is at the maximum just as it's leaving the table. B, its kinetic energy is at the maximum just before it hits the floor. C, its kinetic energy is equal to its potential energy at a point halfway between the table and the floor. D, its potential energy is reduced. E, all the above are true.
I think it's B.
Think it's B?
I only remember because I think this was on the last test as well.
Anyone else? Want to take a gamble? A lot of these were on the last test. Yeah? What we'll do, we'll skip to the other ones that are going to be on the new test then. So after that. Okay. So I get one that says all of the statements are true. Actually, all of the statements are true. So we know that the potential energy is going to be the max when it's at the highest part of the table. We know that the kinetic energy is going to be at its max just before it's going to hit the ground. Halfway between the two, they're going to be equal to each other. And then we know that initially the potential energy is going to be its max at the highest part. As it's falling, it's going to be reducing its potential energy. So the correct answer is E, all the above. So let's see if we can work through some problems since you guys said that these were all on the exam last time. So let's go to the new stuff. Should be down here somewhere. And we'll work our way up. Probably the easiest way. New stuff. Here's all the new stuff. Okay. So which of the following is a process for which synthetic radioactive samples are used? Medical, application, food preservation, studies of piston wear, monitoring, can't even talk, monitoring the progress of certain oils through pipelines, all the above. And this is chapter 20. Okay, we got an E. Do you guys agree with E?
Yes.
E is correct. So we know that a lot of times when they're fighting cancer, they're going to use a radioisotope to sit there and do that. So medical applications. When you're trying to preserve certain foods, you're trying to kill off everything else. So that's a good way of, again, using radio active material. When you're trying to make progress of certain things moving through systems, it's easier to see a radioactive material because you can use a Geiger counter and it'll radiate even through some of the pipes that we use. All of the above. Okay. Number 61. Which of the following statement is the best comparison of chemical properties of oxygen 15 and oxygen 16? A, reactivity of the heavier element will be greater with oxygen 16. The reactivity of the heavier element will be greater with oxygen 15. Oxygen 16 will undergo more frequent reactions. Oxygen 15 will undergo more frequent reactions. There is no difference between the chemical properties of the two isotopes. What do you guys think? Now, the key here is this: chemical properties. So we know when we talk about isotopes, chemically they're going to behave the same way. Nuclearly, they're going to be different. Okay. So when we talk about the nuclear aspect of things, that's how they're going to differ when we're talking about isotopes. Okay. Chemically, they're going to be the same. So then what do you guys think the answer is now? That's right. It's E. Okay. 60. The half-life of 239, uranium 239, is 24 minutes. A freshly prepared sample is allowed to sit for 2 hours. If the mass of the sample after the period of time is 1.0 milligrams, what was the original mass of the sample? Okay, so this is going to be looking at the half-life. There's an equation that you guys can use. R is going to be equal to S 1/2 see, I'm trying to remember so this will be half-life. 1/2. I'm going to use N because I can't remember it, where N represents the number of half-lives that it goes through. So if we're going for 2 hours, we know that 2 hours is going to end up being a total of how many minutes? So 2 hours, 2 hours is a total of, isn't that 180? I mean, 120 minutes?
Yes.
Okay. Okay, so then we're going to divide that by 24 minutes, and that's going to give us the number of half-lives it goes through. Let's write out what this equation means so that you guys will remember. And you may want to, so I'm giving you guys for this exam, for your next exams, I'll give you guys a page front and back of the cheat sheet or a information sheet. So R is going to be the remaining. The S is going to be our starting amount. The N is going to equal number of half-lives. The way you calculate your N so it's the half-life, time divided by the half-life. Okay, so in this case, it's 120 divided by 24. I believe that's 5. Check my math. Okay, and so in this case, we know that we're going to end up, our remaining was 1. So we're going to go ahead and plug that in this equation. And we're trying to solve for S. And we know that 1/2 and that's going to be to the 5th power. So in other words, that's going to be 2 times 2 times 2 times 2 times 2. So that's what? 4, 8, 16, 32. So that's going to be 1/32. Oops. And this is an S. Sorry. So if we solve for S, S is going to be equal to, multiply both sides by 32. So that we could get the S by itself. So we get S is equal to 1 times 32. So that's just 32 milligrams. Okay, questions? Okay, good job. Okay, which of the following correctly matches the principal forms of radioactivity emissions with their respective electrical charge? Okay, so we're looking for the respectable electrical charge. So we have alpha particles, beta particles, and gamma particles. Okay, now we want to think about the charges that an alpha particle is going to have. What do you guys think the alpha particle is going to have? So alpha is the Greek letter for A, right? And so A comes to the first of the alphabet. Have you guys ever told anybody bad news before?
Yes.
Yes. Okay. So the way I was taught about telling people bad news, you want to tell them something good first, and then you want to tell them something bad. Okay. Okay. So alpha is always going to be positive because, good news. Okay. So that's always going to be a positive value. So what do you think beta is going to be?
Negative?
Beta is going to be negative. Okay. And then gamma is not going to have a charge. Okay. So gamma radiation, it doesn't veer when you put it in like an electromagnetic field. Electromagnetic fields puts a plus and a minus charge on things. And so the alpha particle is going to go towards the negative because it's positive, and the beta particle is going to go towards the positive because it's negative. Okay. So the correct answer is Oh, and I like that. Bad news, negative. Yeah. So B is for bad news, negative. Okay. So alpha is positive, B, beta is negative, and gamma is no charge. Okay. You guys got it? Okay, good. Caitlin, did you get your check your email?
Yes, I did. Thank you so much.
No problem. Yeah, believe me, I know about having technical issues.
Right. I don't know what my computer was doing today, but it just did not want to work.
Yeah,
It's slowly chugging along right now.
yeah. I'm using my work one, and there are points where I can't get it to move the way I want to, so I have to use like other little tricks that I know to try to get things to work on it because my buttons are not working the way they're supposed to be working. So okay, oh, I got carried away. Let's see. So which of the following statements is slash are correct? A chain reaction is a reaction that that has a product one of its own reactant. Okay. Chain reaction is a reaction that has a product one its own reactants. Okay. The critical mass of an element is the minimal mass necessary to reach a to react with a trans-uranium element. 3, a breeder reactor is a device whose purpose is to produce visible, let's see, fissionable fuel from non-fissionable isotopes. Any guesses?
I'm gonna guess C.
You're gonna guess C? Okay. Okay. Anyone else? Okay. So we have the first one and we have the last one. Okay. So Sol actually had made a valid point. If we put some commas in there, it actually makes sense. So I need to fix the question. In other words, so actually the correct answer is going to be the first one and the third one. So 1 and 3 are your correct answers. The second one is incorrect. Critical mass is going to be the critical mass of an element is going to be the minimal amount of mass that you can get a product from a trans not a so instead of reacting with a trans uranium element, it's going to be the smallest amount that you can get a feasible product from. Okay. Let's see. Does that, is that clear? So it's the first one. That first one is the correct answer. Okay, here we go. So which of the following units is the most commonly used unit? Which of the following units is the most commonly used to express radiation exposure? Any thoughts? Do you guys think it's REM, REM, R, J, RAD? That is correct. REM is the correct answer. So we know joules represents energy. I'm not sure what they're going to mean by the R, but rad can be used for radiation, but it's not commonly used. Um, so REM is the correct answer. What's wrong? Okay, let's see. I'm gonna have to shrink this a little bit to get the full question in. Actually, a lot. Well, we'll expand it. Okay, so here's our flame test. Okay, you guys didn't do a flame test in your lab, but so above are the results from a flame test that you've done. Let's see if you've been given an unknown. If you've been given, let's see, you've been given, and it should be an unknown, typo there. Sorry about that. And unknown to identify. Your unknown burnt red. Okay, so let's use this table. We're looking for red, stuff that's red. Okay, so we have two possibilities that are red, or actually we have three possibilities. So we have lithium, we have strontium, we have uh, radium, and that's it. Okay, now by doing this reaction, you determine it was an alkaline metal. Okay, so we know it's an alkaline metal. So are any of these alkaline metals?
Would the strontium and radium be alkaline metal?
That's right. So they're both group 2 metals. So these two. Okay. So you could have, in this case, given me either one and you would have gotten the correct answer. Okay. So we know that it's a red wavelength that we're looking for. So we're looking for red. So where does red fall into place? So red is the range from 625 to 740. So you determined that the flame of the unknown was red. That would be a wavelength of, and here are your choices, 700 nanometers, 550 nanometers, or 400 nanometers.
Should be 700.
That's right, it should be 700. That's correct. Because that's where red is falling in between, right? And how many sig figs should that be? So for 700. That's right. 4. Yeah. Sorry. Somebody typed it in the chat first. My apologies for cutting you off. Okay, so we have 4 sig figs, right? Because we have the decimal there. That means that that 0 is going to be significant in this case. That's 1, 2, 3, 4. Okay, so let's see. Calculate the frequency emitted from your unknown if the speed of light is 3.00 times 10 to the 8th meters per second. Let's see. Show your work and box the answer in your scratch paper and upload your work for points, for other points. Okay, so like questions like these, when they're short answer questions and you just have to fill in the box, it's cool for you to fill in the box, but if you show your work, if you make a mistake, I can give you some partial points, right? Because a lot of times it's a calculation mistake rather than anything else. So that's why I'd like you guys to upload all your work at the end. Okay, so do you guys remember the equation that we're going to be using for this? Anyone? How about C is going to be equal to lambda nu? This is one of those equations that you may want to have on your sheet. Okay, so in this case, we know that C is going to represent the speed of light. Speed of light is given to you. So that's going to be 3.00 times 10 to the 8th. That's meters per second. And then lambda, so that's going to equal wavelength. And nu, that's going to equal frequency. So we know our wavelength from up here. It's red wavelength, so that's going to be 700 nanometers. Now, if we look at our speed of light, that's going to be in meters per second, and this in nanometers. So anytime that you're doing calculations, you want to make sure your units match. So either you want to change your meters to nanometers, or you want to change your nanometers to meters. So let's go ahead and change our nanometers to meters. So if we have 700.0 nanometers, anybody know the conversion from nanometers? So for every 1 meter, that's going to be the same thing as having 10 to the 9th nanometers. So I use, since 9 starts with the N and nanometer starts with an N, so I always remember it because 9 starts with an N. So 10 to the 9th nanometers will equal 1 meter. So if we do this, the math, you'd end up with equals 7.000 times 10 to the -7 meters. Okay, so then now we can plug this into our equation. I'm going to pull this down. Actually, I'm going to find you that this is the speed of light. Okay. Okay, so we're going to go ahead and plug in what we know. Okay, so in other words, here we need to solve for nu. So we're going to get nu by itself. And so we're going to divide both sides by the 7.005, right? 7.00 times 10 to the minus 7 meters. Okay, so then our meters are going to cancel out. And we end up with our value. So our bottom number has 4 sig figs. This guy has 3 sig figs. So altogether, we should have a total of 3 sig figs. So it'll be 4.29 times 10 to the, and then that would be either, it'll be written as seconds to the minus 1 power, or it could be written as 1 over seconds, or it could be written as hertz. In terms of the units, they would all mean the same. Okay. Questions? Okay. Let's keep going. Let's keep going. See how many more we can get knocked out of the way. Okay. So let's do this table, guys. Should be an easy one, right? Okay, so here in the second column, we have SR2 plus. So it's strontium 2 plus, or strontium 89 ion. Okay. So then how many, what would be the atomic mass of this ion?
89.
Okay. Yes, so that is correct. That would be the final answer. So you're right. 89 would be the mass. And that's Ashley, right?
Sorry, yes.
Yeah, okay. And then how many protons? Anyone?
Is it 51?
Okay. So we're talking about protons, right? So protons are going to be given to us here. It's also our atomic numbers. So the atomic number defines the element, which is also the number of protons. And that's never going to change. But you're getting ahead of yourself because the number of neutrons is going to be the difference. right?
Oh, okay.
This guy is going to be 38. Then if we take 89 minus 38, that's going to equal 51. So our number of neutrons is going to be 51.
Would you have to take into consideration the 2 plus or no?
So the 2 plus would represent the number of electrons. That's the only thing that it's going to affect.
Oh, okay.
But good question. When we're looking at that, we know that this side here, this is going to be pertinent for our number of electrons. This side here is going to affect our number of neutrons, and our protons are always going to be the same. Protons are always going to be the same for that element. Okay. And for the exam, when you guys take the exam, make sure that you guys use that tab to get to the empty boxes. Even though I have that written up there, a lot of people still have trouble with it. And I haven't figured out how to make it so that it fits in the question box yet. Okay, so the next one, let's see. We know that we have 16 protons, right? So whatever this is going to be, it's going to have a 16 at the bottom here. Okay, so then what we're going to do, that means we also know that if there's 16 protons, what will be the atomic number? Okay, what did I just say about the atomic number? Take a look at the one above it. It's going to be 16. That's right. So we're going to have 16 here. So let's go to our periodic table. So we're looking for the atomic number 16. Let's see, 16. That's sulfur. Okay, so then we know that 16 is going to be sulfur. So here we're going to put an S. Fix my 16. So we're looking 16. Okay, so then if we have 16 protons, how many neutrons must we have? Okay, so we have our atomic mass. Can we use that to determine the number of neutrons?
Yes, you would subtract the protons, is it?
Okay, that's right. So that's what, 19?
Mhm.
So we have 19 neutrons. And so then our mass number is going to be 35. Same as our atomic mass. Okay. So number of electrons are going to be the same. So we don't have to worry about it having a charge. So then we can call this, you could write it as, this one, it'll be hard to type unless you use a special way to write. And I'm going to see if I can actually add that on there to the questions. So what you guys can write it as, you could just type it as sulfur 16. Okay. Okay, the last one is thorium 235 ion. Okay, so we have the thorium 235 Roman numeral 3 ion. So let's see. What would be the atomic number?
90?
All right, 90. What would be the number of protons?
90?
What would be the number of electrons? Here it says plus 3. So if it's a +3, that means we're removing 3 electrons. So how many electrons do we have left? That's right, 87. Good job. So when we talk about this +3, we know that the electrons initially, when it's 0, they have to be even to the number of protons because it has a 0 charge on it. As soon as you remove 3 electrons, so if you have +3, that means you're removing 3 electrons. That means it's 87. If you're adding electrons, you're going to have a negative charge to it, okay, because electrons are negative. Okay, not too bad. You guys just a little rusty. Okay, we're going to keep moving. Okay, so this is we're going to be talking about some forces and stuff like that. Okay, so we have chlorine and hydrogen. So the question says, examine the structure below. Which of the following is the most important interactive force experience between the molecule and its identical molecule? So we're talking about two molecules interacting together. So the first one is hydrogen bonds. Okay, so let me give you guys a little input about hydrogen bonds. So hydrogen bonds are only going to occur when you have hydrogen bonded to nitrogen, oxygen, or fluorine. Okay. And it's going to be an interaction between two different molecules. So both of them, like in this case, we have water here. You're going to form a hydrogen bond between the two water molecules. And the hydrogen bond is not a true bond, it's more of an interaction. It's like a fist bump, but it's a pretty strong fist bump. You know, you keep that connection. So that would be the bond between the two. Okay. So that will be a hydrogen bond. Now, this guy, what it does, it actually forms a dipole. So what happens is that the electrons are going to be spending a little bit more time around chlorine than it's going to be spending around the hydrogen. So in that case, the electron is going to spend more time on this side of the atom than on this side of the atom. So this guy is going to have what we call a partial negative charge, and this guy is going to have a partial positive charge. Different than what we see with like sodium chloride, where sodium is plus and chloride is minus. And so they're interacting only on electrostatic forces. So this guy is going to have dipole-dipole forces. Okay. And in the case of induced dipole, it's when you put something that has a charge or something that has a strong dipole next to another something that has a dipole, and you're pulling the electron to favor one side or the other. So the correct answer, the one that's going to be the most important force for this reaction, is going to be your dipole forces. So that's where you're going to be using your, do you guys have your packet? Let me pull that up.
Yes.
Yeah. See if I can find my packet. Okay, perfect. It like went right to what we were looking at, what I wanted to look at. So here, this basically shows us, right? So we had chlorine and hydrogen. And so you look at the difference between those two. Since the difference between those two is is 0. I'm sorry, 1 is 1 is the difference between those two. Now, when it's 1, let me type this out for you guys too. If your This is called your electronegativity. So if your electronegativity, the difference between your electronegativity is going to be uh, less than 0.5, then it's going to be nonpolar. So in this case, that's going to be no dipole. If your electronegativity is between 0.5 or equal to 0.5, but less than or equal to 1.8, it's going to be polar. And it's going to form a dipole. And then in the case of it being greater than 1.8, it's going to have ionic character. Okay, so our difference here between our H and our Cl, sorry, H and our Cl. So that one is going to be a 1.0. So then that's going to have dipole. We know that if we have hydrogen and fluorine, or hydrogen and oxygen, or hydrogen and nitrogen, all of those are going to form hydrogen bonds. Okay, so the correct answer for that one is, again, dipole forces. Okay, so if a substance X has a strong intermolecular attraction, has a stronger intermolecular attraction than substance Y, which of the following is the most apt to be false? So we have two substances. So Y has a lower melting point. Y has a lower boiling point and a higher vapor pressure. Y has a higher vapor pressure and a lower molar heat of vaporization. Y has a higher boiling point and a higher molar heat of vaporization. X has a higher boiling point and a higher molar heat of vaporization. And then X has a lower vapor pressure and a higher molar heat of vaporization. Okay, so let me see how I can explain this. So if your intermolecular forces are stronger, so when you're in the liquid phase, you're still interacting because of those intermolecular forces. When you're in the freezing phase, you're interacting because of those molecular forces. So the stronger your molecular forces are, the higher your your boiling point is going to be. Okay, so it's going to take more energy to take to disrupt or to separate a molecule if you have strong forces that are keeping you together. Does that make sense? Okay, so if we think about this, right? So the higher your forces are, the lower your vapor pressure is going to be, because vapor pressure occurs because you're able to break loose, right? So if you have a lower boiling point, you're going to have a higher vapor vapor pressure. Okay. And then if you have a higher boiling point, you're going to have a lower vapor pressure. Okay. And then when we talk about the heat of vaporization, that's just the heat that it takes to make vapor. So if you're strongly connected, is it going to be harder to make vapor, or is it going to be easier to make vapor? Anyone there? You got a 50-50 chance. Take a guess. Let me see if I can draw it out. Okay, so we have, this is going to be our X solution right here. This is going to be our Y solution, the baby boom. Okay, now they told us that X is stronger, right? So since X is stronger, it's going to take more energy I could spell to make it a gas. It's also going to have a higher boiling point and a
So
lower. Oh, go
sorry,
ahead.
would it be D?
Okay. So we're looking for the thing that's going to make it false, right?
Oh, okay. Okay, I didn't see that.
False. Yeah. And it's going to have a lower vapor pressure. Okay. So then Y, what do you guys think is going to happen with Y? Since it's weaker, it has weaker. Is it going to take more energy to make it a gas? So it's going to take less energy to make it a gas.
So it'd be a lower boiling point.
It also is going to have a lower boiling point. That's right. Okay, we have a lower boiling point. And it's going to have higher vaporization or vapor pressure. Okay, so now we need to find the one that is the opposite of what we're saying here, right? So which one is the opposite of what we're saying here?
B?
B. Is that true? Higher pressure. So does Y have higher vapor pressure?
It does, but
It
it's
does,
lower.
right? So, but it has low molar heat. So that's lower energy, right? I guess that's what I should say. So it has less energy to make it a gas. So this represents the energy. The heat of vaporization is our energy. So it has a lower energy. So, but first part of it, higher vape and lower energy. Well, isn't that less energy and higher vape? So isn't that true?
Yes.
So that one would be true. So we know that that's not the correct answer. Okay. We know that, what was the one that we looked at earlier? You said E, right? That one had lower vape and higher energy, lower vape. So we know that that's also true. Okay. Because we're trying to make it false. Okay. What do you guys think it is now? Higher boiling pressure, higher boiling point. You guys think that one? Ah, so Sol says C. You guys think that one is correct? It says Y has a higher boiling point and a higher vape. So we know that Y has a less, and then, I'm sorry, less energy. So that's our heat of vaporization, and it has a lower boiling point. So that would be false. And so that would be correct. That's our correct answer. So C is our correct answer. Does that make sense?
Yes.
Okay. Yeah, I've got to do a better job of going over the forces in lecture. I realized I didn't do a good job on that one. Okay. So the ratio of anions to cations in an atomic compound is always such that the compound is reduced in size when compared to the parent atom. B, there are as many anions as there are cations. C, the anions outnumber the cations. D, the cations outnumber the anions. Or E, the compound is electrically neutral. Okay, so we're talking about ionic compounds. Ionic compounds means that you have two ions. So what is the rule about ions? So like say, for instance, if we have sodium chloride, well, we know that the sodium gives up its electron to the chloride. So sodium is actually Na plus, and then the chloride is going to be Cl minus. Sodium loses that electron, chlorine gains that electron. They come together because of the charges and they neutralize each other. So what do you guys think the correct answer is? Do they have to be the same number of each other? Can I also have, let's say, magnesium chloride, which is MgCl2? Are those going to be the same number to each other? A 1-to-1 ratio? Okay. So the correct answer is E. And the reason why it's E is because the charges have to balance each other out in an ionic compound. So our sodium charge has to end up equaling our chlorine charge. Okay. So we know, and if you guys look at some of these later lectures that we just did 2 weeks ago, I think. Is it my table? Sorry. Okay, so group 17, these guys are going to always, because they're one away from being a noble gas, they're going to always want one electron. So they're going to take that electron from their partner. Sodium, since neon is the nearest noble gas, it's going to want to get rid of one electron so it can be like neon. So it's going to end up being Na plus. And then chlorine is going to be Cl minus. Okay, the charges have to balance out. So let's say if I have oxygen, oxygen is 2 away, oxygen is O2. I mean, it's sorry, not O2, it's O2 minus because it's gaining 2 electrons. Okay, so that means if it pairs up with sodium, then we're going to need 2 sodium because sodium is always going to have a plus 1 plus charge. So then our compound is going to be Na2O. Okay, and so we want to balance the charges when we're talking about ionic compounds. Okay, so again, this guy is going to be a minus charge. These guys here, this is going to be a 2 minus, and then this guy, these two are going to be a 3 minus. And then sometimes you get chlorine or silicone, they're going to end up being 4 minus. These guys here, aluminum particularly, that's going to be 3 plus. Because they're going to be willing to lose up 3 electrons. These guys here, they're going to be 2 plus. And then these guys are just going to be plus. In group 1. Okay. So here we're looking at the electronegativity of lithium and hydrogen. And then we're looking at the electronegativity of hydrogen and chlorine. Okay, these are the values of our electronegativity. They give them to you, so you don't need the table, but you have the table if you need it. So it says, which of the elements will act as the negative pole in each of the following bonds? So we have lithium and hydrogen. So lithium is going to be 1.0. Hydrogen is 2.1. So the one that has the bigger value is typically going to act as the negative pole, right? So in this case, which one has the bigger value, lithium or hydrogen?
Hydrogen.
Hydrogen. So we say we can get rid of these first. Oops. So those are not correct, right? Because both of those say lithium. So here it would be hydrogen. Okay, so now in the case of hydrogen and carbon, which one has the higher value?
Carbon.
Okay, so then our correct answer would be this guy. Okay, does that make sense?
Yes.
Let's see. Still had a question. So an ionic compound means components are charged and not the compound itself. That is correct. So when we talk about an ionic compound, the elements in there or your cation and your anion. Cation is positive, anion is negative. When they come together, they have to balance each other out. So yes, the compound is neutral. So if we leave the term ion on it, that means it has a charge associated. Okay. Good question. Okay, so which of the following correctly describes a covalent bond? A, the charged clouds of the 1s orbital repels one another. B, the charge density of electrons is concentrated between the two nuclei. C, the electron cloud do not overlap as much as it does an ionic bond. D, all available electrons go into the electron cloud of only one of the atoms. And then E, there are no valence electrons. The correct answer is B. That is the closest. Still kind of weak, but yeah. Correct answer is B. Good job. So in the case of covalent, we're sharing electrons. So then that electron cloud is going to be between the two atoms since they're sharing the electrons. Okay, so we're going to do this in terms of increasing polarity. Okay, so they gave us our polarity values, and so we want to set these guys up in terms of our increasing polarity. So we have hydrogen bonding to carbon, chlorine, fluorine, and then we have the case where we have carbon and chlorine bonded together. So we want to put them in order, okay? So all you need to do is basically take the difference. You always want to put the one that is the largest first. So let's start off with fluorine and hydrogen. So we got fluorine and hydrogen. Yep. So we take the one that has a bigger value, and then we subtract the one that has a smaller value. So what is that? 1.9. Okay. And then if we do hydrogen and chlorine, so then that's that's 3.0 minus 2.1. And then we have hydrogen and carbon. And then that's going to be -2.5 minus 2.1, 0.4. And then we have chlorine and carbon. Chlorine and carbon. So then that's going to be carbon and chlorine, 3.1 minus 2.5. Okay, so the way I remember with the increasing sign or the capture sign, I normally remember Pac-Man, but you could say the alligator eats the bigger one. So we want our smallest one, which is going to be our carbon and hydrogen. So that one's going to be the smallest. And then we're going to have carbon and chlorine. And then we're going to have hydrogen and chlorine. And then we're going to have hydrogen and fluorine. So the one that has the increasing polarity, highest polarity, is going to be our fluorine and hydrogen. The smallest one is going to be our carbon and hydrogen. So it's this guy. Questions? How are your brains? Are they fried yet?
Yes.
Yes. Okay. Well, we're going to see if we can give you guys 2 more questions in there before our time is up. So your practice exam, you'll notice it has more questions than you guys have on your real exam. The reason I do that so you guys get a little more exposure. Let's see. So which of the following statement correctly describes ionic compounds? 1, they never contain covalent bonds. 2, they only form when atoms share their valence electrons. 3, they're usually solids at room temperature. 4, they are generally gases at ice water temperatures. So we're saying the ones that are correct. You guys think the first one is correct? Let's get rid of the ones that we know that aren't correct. Anybody thinks that I is correct? Anybody think that I is wrong? Incorrect. Okay, no answers on I. How about I? Okay, so we have one person that thinks that they're correct. That's correct. Okay, so let's talk about that one first. So it says they never contain covalent bonds. Well, if we think about our polyatomic ions, so sulfur or sulfate, sorry, sulfate is an anion, and it can pair up with sodium, which has a plus. So I'm going to need 2 sodiums to match up for that sulfate. So my chemical formula is going to be Na2SO4. Okay, and we call that guy sodium sulfate. Okay, now this polyatomic ion is covalently bonded. So this is a covalently bonded anion, and then our metal is it's a metallic ion. So in this case, it's our cation since it's positive. Okay, now they have to balance each other out. So in this case, we do have covalent bonds in this ionic compound because this is covalently bonded together, but these guys are ionically bonded together. So you can have both. So that one technically is correct. Well, it isn't correct. It's incorrect. So we know that that one isn't correct. Okay, so good. So the correct answer, the only correct answer is going to be 3. So it's going to be only 3 is correct. Because the second one, it says that they share their valence electrons. Well, they're not sharing. Sodium gives up its electron so that the sulfate could have it, right? So there's no sharing that's going on there. One is giving up in this case, and then here, these guys are sharing, but these guys aren't, okay? So then the last one, it says that they're generally gases at ice water temperature. So that's not true. They're typically solids at that. So they're usually solids at room temperature, and below they're going to remain solids. Okay. So match each of the following terms with the appropriate bond type. Okay. So it says it's all kind of screwed up, but electron donating, electron sharing, and delocalized electron. So who's donating electron? Is it going to be an ionic bond, or is it going to be a covalent bond, or is it going to be a metallic bond? Donating electron. In other words, who's giving up electrons? Are electrons given up in covalent bonding, or ionic bonding, or metallic bonding? Ionic, that's right. So this one should go, ionic should go with this one. So then we can get rid of all of these because they don't start with that. So this is the 2. Okay, so the next one, electron sharing. So is that going to be ionic? Well, we already know it's not ionic. So is it going to be covalent or metallic? Covalent. Okay, so then the correct answer is that. So when we talk about metallic bonds, only thing that's happening is that you're delocalizing your electrons. So the correct answer is E. And by the way, this is chapter 12. And chapter 6 is nomenclature. So, okay, examine the following model. What type of bond does this say? What type of bonding does this model represent? Now, look at it. This is the atom, and then it loses its electron or delocalize its electron. So what type of bonding do you guys think this is? Think about what we just said down here. That's right, metallic. Okay, so we've already done electronegativity. Do you guys want to do one more? This will be the last one. We'll do electron configuration. Okay. Okay, so what we're going to do, we'll do this last problem here. This is a good one too, because this is the one that always ends up popping up. So I'm going to type those out here, and then we're going to go to the periodic table. And I'm sorry, I can't do the superscript in Zoom yet. I haven't figured out how to do that. And subscript. Okay. Okay, so here's our periodic table, right? So what we're going to do is I'm going to pull over our questions here first. Okay, so we're going to be doing LR6 plus, AS3 minus, and PT. So let's start off with the PT because that's normal. It's not an ionic compound. So what we need to know is that here, this is going to represent our S subshell. So I'm going to make it a cursive S. This here is going to be our P subshell. This here is our D subshell. And then this down here is our F subshell. It's right here. Now these guys here, they're really in the D, right? So they're really in these spots right here. So these two really belong in these spots right here. Okay. So when we start talking about our electron configuration, we're just trying to keep track of all the electrons in a compound. I'm going to show you the short way because we're like well above time than we're supposed to be. And then if you guys are interested, I can show you the long way. Short way is always better because then you don't have to worry about writing everything out. And I accept both of them. So in this case, what we're going to do is we're going to find PT on our periodic table. So PT is atomic number 78. Okay. The first thing that we're going to do is identify the noble gas that is before PT. So we're going to go ahead and write down. If I write it up here, can you guys see it? You see my PT written up top? Okay. Okay, we're going to write the nearest noble gas that we've passed, right? So PT, so you want to go back. So then our nearest noble gas that we've already passed would be xenon. So we're going to write brackets, xenon. So that basically means that we have all of the electrons that xenon would normally have. And then we'll start right here. So when we start right here, we're starting in the 6th period, and the very first subshell is S. The S has 2 spots. So that's 1, 2. So in this case, we're trying to get to platinum. So we're going to count so we can get to platinum. So the very first one that we have is going to be 6s2. Okay, so the 6 tells us the period that we're in. It tells us the subshell that we're in, and the 2 tells us how many electrons that are there. It can only hold 2 electrons. So that's where the 2 is at. So then that takes care of these guys here. So then we're going to come down here, right? Because you want to follow the atomic number. So we have 55, 56, and then here's 57. So this guy is the F subshell. Now, the funny thing about the F subshell is going to be different. It's not going to still be at the 6. It's going to be 2 below the 6. So this is going to start off at 4F. And if it were me, I'd write that on my periodic table so I remember that. So it starts off at 4F. These guys are going to be completely full because we're trying to get to platinum. We're trying to get to platinum. So 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the F sublevel only holds 14 electrons. So then we would put 4F 14. Okay, so that takes care of this one. And I told you that this guy's really a D. Now the D starts here at 3D. And so we're going to be coming up here. We've gone through all of these. Then we're going to be coming back up to this one, right? So this here, this is the 3D. This is the 4D. This is the 5D. So right here would be the 5D. Okay, so then we would have 5D. And so we have the one that's here, that's really in that spot right here. So that's 1, 2, 3, 4, 5, 6, 7, 8. 5D8. Okay, so this is the way that you would normally do it. Now, if you click on palladium, right, it will actually let us know that there's something different going on. So these numbers here, they're representing each of the periods and how many electrons are in those periods. So in this case, this guy has in the 1s, it has 1s2. This would be our 2s. So then, our second period. So then that would be, there's 8 of them. So you'd have 2s. So that would be the 2 electrons in the 2s. And then you have 2s. P, and the P holds 6. 1, 2, 3, 4, 5, 6. Okay. Then we would have 3s2, 3p6. That would be a total of 8. But we have 18. So that means that we also have the 3D, which has 10. 3D, 10. Then the 4 has 4. Sorry to continue down the line. Normally I'd write them all the way across. 4s2, 4p6. So that's a total of 8. And then we have 4d10. So that's a total of 18. And then we have 4f14. So that's a total of 32. And then this guy's our 5. It has a total of 17. So we have 5s2, 5p6. So that's a total of 8. So then, and then we have 5d, and so 17. So we have 8 plus 5d9. Okay, so that would add up to 17. And then we have 6s. So this would be the correct way of doing it. However, if you did it this way, I would accept this way because most of them work out this way. This one is an exception. Okay, so that's why I did it both of those ways. Okay. And so you'd write all of those in one line, and that would represent, you'd put PT here, and then that would represent the full electron configuration. This here would be the noble gas core, and then everything else. But again, you have this one exception that happens, and unless you know a little more about chemistry and what you guys do, then you guys would have written it this way. That's the normal way of writing. Okay, so let's talk about what happens in the case of an ion. Okay, so like in the case of, let's do the AS, because that one is easier. So we have AS. So normally when we write AS, when it's by itself, we'd go to, do you mind if I erase all the stuff that's down here on my markings so I don't get confused? Okay, so we have our AS. We want to go to the nearest noble gas that's before it. So it will be AR. We're going to put that in bracket. And then we just go through the process again. So AS, so AR. So we come down here to the 4th period. So then it will be 4s2. So that takes care of this. Then it's 3d10 because the D holds 10 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3. And then we have 4p3. Okay. So we're in the 4th period. Now that 4th period is always going to be what we are in for the S and the P. The D is always going to be 1 below than the period. Okay. And then the F is always 2 below. Okay. So then what we really have is we're adding 3 more electrons, right? So the P can hold a total of 6. So it can actually hold all of those electrons. So if we write AS 3 minus, it's going to be AR 4S2 3D10 and 4p6 because we've added 3 more electrons, and that's what that 3 minus represents. Okay? Okay, now when we do the next one, we're also going to do it the short way. So we have LR 6 plus. Okay, so we want to do it as if we're doing LR first. Okay, so we're going to pretend we're doing LR, so we need to find LR. Okay, so we have LR right here, down here. Okay, so we want to follow it back using the atomic numbers. Okay, so that's 89, 88, 87. And then, so our nearest noble gas before it would be radon. Okay, so then we start off at that radon. We're at the 7th period. So then we start off 7s2. Okay, then we follow it back down. We go down. So if this is the 4F at this line, so this is the 5F. 5F. And it's at the very end. So we're taking all 14. For F14, and then we go to that very last one. So then that one is technically in the D, so that's 5D, so that would be the 6D, 6D1. Okay, so now it's losing 6 electrons. So when you take away electrons, you're always going to take away from the higher periods first. So in this case, I'm going to use a different color to kind of help us see that. So we'll take away from the 7 first. So there's 2 in the 7. There's 1 in the D, and then we have 3 that's going to be in the, so we need another 3 to get rid of. 3 that's going to be in the F. So then we have -3. So then we end up with LR 6 plus RN, and then the only thing that will be left will be your 5F. So 14 minus 3 would be 11. And that's it. Okay? Okay. Well, I need to go because I have a presentation for another group. So if you guys have any questions, text me. I'm actually going to extend the exam till this Sunday. It'll say that it's due, I think it's Wednesday or Thursday. It's going to be due on Sunday at 11:59 p.m. Okay? You guys have a good night. And then hopefully I'll see you guys on Thursday.